discuss about Module 4, that is the first IoT hardwares and interfaces. And in that, we are going to discuss architecture of IoT using mobile devices. So, the architecture of IoT using mobile devices typically follows a layered model with mobile devices acting as both data source as well as the gateway and connecting to sensors and uh, network, the cloud, and users. Or data flows from devices or sensor layers through a network layer, which can use mobile technologies like Wi-Fi or Bluetooth, to an IoT gateway or directly to the cloud for processing and analysis. Before being presented to the user via mobile application interface. So this is how the architecture of IoT mobile devices works, and so next is in this architecture of IoT using mobile devices. Uh, the key layers and mobile device roles, we look into these things, which is the device layer, that is perception layer, where mobile devices equipped with built-in sensors like GPS, accelerometer, and cameras collect environmental data. They can also host or connect to other sensors and actuators. And next is the network layer. The network layers or the mobile devices uses various communication protocols like Wi-Fi, Bluetooth, cellular networks, or NFC to transmit data from perception layer to other devices and the cloud. Uh, and next is the IoT gateway layer. In this layer, uh, this is where the smart objects or sensors communicate via the smart objects. They communicate with the other smart objects or integrate with other objects, or it connects to the internet or to the remote head office or central location where the user is based out to collect and process the data. So IoT gateway layer, in this layer, the mobile devices themselves can act as a gateway and aggregating data from connected sensors. So it will collect all the data from the sensors and also provide the pre-processing, filtering, and secure connections to the cloud or the other network components. Cloud layer. In this cloud layer, data from mobile gateways is sent to the cloud for large-scale storage and data processing. This layer leverages big data analytics and machine learning to extract insights and optimize applications. So, the cloud layer is nothing but this is where the central storage is placed, and also the data processing also happens in this cloud layer. And the data in this is used and using the business data analytics and machine learning to extract insights and optimize these applications and make any kind of decisions, all done with the data from that cloud layer. In the application layer, this is where the user interacts. Normally, the application on the device through which the user can interact or see the reports or see view the sensor devices and their statuses likewise. And mobile applications provides a user-friendly interface for monitoring, managing, and controlling IoT devices. So how it works actually? Normally, this IoT layer works data collection and data transmissions, data aggregation and pre-processing, cloud processing and analytics, user interactions. So in this data collection, So data collected from various sensors, the mobile devices with sensors or connected to other sensors capture real-time data from the machines or where this particular sensor is located or fitted or integrated with. From there, it will collect all the data and and it will be captured via the sensors. And data transmission, like this is where the communication happens, like via the gateways. Data is sent over wireless networks like Wi-Fi, Bluetooth, or cellular network to get to a gateway or directly to the cloud. So the data transmission happens via wireless networks or a gateway through the uh, to the direct central location or to the central processing office or the user sitting at the central office where he collates all the data. And data aggregation and pre-processing. So once the data is collected, next thing is to aggregate and collect all the data. So like gateways, including mobile devices, aggregate and pre-process the data before sending it to the cloud. So it will collect all the information and it will process the data and it will send the data across to the cloud. And next is cloud processing and analytics. In this, the cloud performs complex data analysis, like we discussed, big data analysis happening to identify trends, and it can also see at what time uh, what kind of activity happens and how the machine performs. Is there any issues in the production or any delays or any issues or those kind of things can be retrieved from or interpreted from the data and generate actionable insights and store the processed data. Next is user interaction. So normally user interacts with the mobile application to check the status of the uh, data or the sensors or devices. So normally the mobile application displays this data and collected from all the sensors related via from the sensors and allows users to monitor and control connected IoT devices. So architecture of Internet of Things continued. In this, elaborately, I will explain that. Internet of Things IoT technology has a wide range of applications. It can be used in any kind of things. Even nowadays, mobile uses those kind of IoTs because you have a smartwatches which is integrated with the mobile apps, which can tell you the heartbeat or blood pressure and other details, other vitals. Uh, and those are kind of IoT devices what you see, and and the use of the Internet of Things is growing so faster. So it is the networking of physical objects that contains electronic embedded within their architecture to communicate and sense interactions amongst each other or to the external environment. And normally, architecture of IoT are divided into four different layers. One is sensing layer, network layer, and data processing layer, and another one is application layer. So this is a diagram of the architectural diagram of the IoT uh, devices. So on top, the smart application, the application layer happens. The application on the mobile who interacts with and manages the data collected from data processing layer. I'll come from the bottom from sensors. The sensors where the data is are collected, which is physical devices, and it is sent on to the network layer or an internet gateway via which this particular data is sent to the central data processing unit or to the data processing layer. In this data processing layer, it might be located in the cloud where the data are processed and used for data analytics and decision making and to identify any issues or any kind of trends. So all kind of things happens over here in the data processing. And the application layer where you can see the data and you can interpret the data and you can do the analytical data to check the trends and understand the demand and supply and etc. or the performance of the machine, etc. So what this sensing layer? This sensing layer is the first layer of the Internet of Things architecture and is responsible for collecting data from different sources. The sensor collects data from different sources. For example, the layer includes sensors, actuators, that are placed in the environment to gather information about temperature, humidity, light, sound, and other physical parameters. Wired or wireless communication protocols connect these devices to the network layer. And the network layer of IoT architecture is responsible for providing communication and connectivity between devices in the IoT system. So this network layer provides the connectivity of the Internet of Things devices or sensors in the system, and it also helps to connect to the Wi-Fi gateways, and also it helps to connect to the central processing data processing unit or data processing layer. And it includes protocols and technologies that enable devices to connect and communicate with each other, and with the wider internet. Examples of network technologies that are commonly used in IoT include Wi-Fi, Bluetooth, Zigbee, and cellular networks such as 4G and 5G technologies. Additionally, the network layer may include gateways and routers, etc., etc. That acts as an intermediary between devices and wider internet, and may also include security features such as encryption and authentication to protect against unauthorized actions. So data processing layer. In the data processing layer, the data processing layer of IoT architecture refers to the software and hardware components that are responsible for collecting, analyzing, and interpreting data from IoT devices. So, like I explained, this data processing layer where it collects the data from all the sensor devices via the network layer, via the internet gateways. And collects all the data, and it process, analyze, and we can make decisions based on that, and everything. So we using the machine learning algorithm, you can perform the analytics, data analytics, and data management. So how to make extract meaningful information from the insight from the data and make decision based on that. Application layer. The application layer of IoT architecture is the topmost layer, that is where a user interacts with the sensor or other layers via the applications on the mobile or on the computer. So it is responsible for providing user-friendly, like application will be user-friendly interface and functionality that enables users to access and control IoT devices, and whatever in the data processing layer happen, the data analytics and insights can be viewed in this application layers. So you can visualize the data, and you can have like visualization tools or charts like that, or you can see the trends, graphs, etc., etc. Can be seen in this application if that particular feature is included in that application. So advantages of IoT. What are the advantages of IoT? Execute multiple tasks at a time, like a computer. Easiest internet connectivity, and works on GUI, that is graphical user interface mode, because of HDMI port. Best suited for server-based application that can be connected via SSH secure shell to access the RPA command line remotely, and file sharing with via FTP file transfer protocol, more reliable for software applications. And disadvantages of IoT, security concerns and potential for hacking or data breaches, uh, privacy issues related to the collection and use of personal data, and dependence on technology, and potential for system failures, limited standardization and interoperability among devices, complexity and increased maintenance requirements, high initial investment costs, limited battery life on some devices, concerns about job displacement due to automation, limited regulations, and legal framework for IoTs, which can lead to confusion and uncertainty. Modern applications of IoTs. So, what are the modern applications of IoTs? In this, smart grids and energy savings, smart cities, smart homes or home automation, healthcare, earthquake detection, radiation detection, hazardous gas detection, smartphone detection, and water flow monitors, traffic monitoring, and robots and drones, smart door lock protection system, healthcare and hospitals, telemedicine applications, biochip transponders for animals in farm, and heart monitoring plans, example pacemaker, ECG, real-time tracking, and other devices. In this mobile as an IoT gateway, so how the mobile acts as an IoT gateway, we see little more detail about this. The next, this is called the next giant leap in IoT architecture. So IoT gateway is an indispensable part of Internet of Things architecture. So it is very essential for the uh, communication of the sensors with the central processing unit or with other sensors or other smart objects. IoT gateway brings IoT networks to life. Without IoT gateways and now without IoT mobile app development, the wild west of IoT devices cannot connect with sophisticated IT world. And so this is the demonstration how the IoT devices, source sensors, the smart objects collect the data from the sources and communicates to the IoT gateways and IoT clouds. And for connecting it to the IoT gateways, these are the protocols it uses, which are RFID protocols, technologies, Wi-Fi technology, Bluetooth, NFC protocols. These are the protocols it uses to connect to the IoT gateways. So this is an approximate estimation sometime back they have published. How many IoT devices will be added every minute? 1,52,200 IoT devices every year, 5,25,600 is the projected. And IoT devices by 2025, end of 2025, you will have nearly 80 billion IoT devices live. It will be across the globe. So next is any physical thing or device, sensors, actuators, objects, meters, displays, and so on, connect, etc. connects into IoT network through many ways. So one is direct connectivity between the device and IoT platforms, connect through an IoT mesh network, connect to an IoT gateway, no connectivity. So, if you imagine a humidifier reports moisture level every seconds, uh, what imagine if the each and every reading is sent to the cloud, and naturally the amount of data from one device would go massive. Multiply that by billions of devices of, and not every piece of data is taken into use for analysis. And companies use a subset of data for viewing or further analysis, and that's where what happens is data filters comes in, and data filtering is just one of the tasks that an IoT gateway performs. An IoT gateway does many other tasks as follows. One of those tasks are protocol conversion and local decision making, local filtering and aggregation of data, and applications, functions not delivering by the IoT endpoint, communication to the cloud and IoT platforms, local additional processing power and storage, local security. Why do you need an IoT gateway? A network of a physical thing or device is the most obvious layer in IoT architecture, but those physical things or devices have limited connectivity capabilities. Sensors use Bluetooth, low energy, really for low power wireless communications or ZigBee, local area network LAN, home area network HAN, and personal area network band. These protocols cannot directly connect to larger networks like wide area networks WAN or the internet. That is why an IoT gateway is essential. It offers sensors a single point of contact with external networks using Wi-Fi, GSM, Bluetooth, or other types of connectivity. Our smartphones already have these capabilities inbuilt. The combination of massive wireless connectivity and rich cellular networks provides uninterrupted access to the internet On the other hand, the tsunami of embedded, like tiny low-power wearables like watches, smartwatches, IoT, and many more devices cannot enjoy the same level of universal access to the internet. So for these kind of deviations or differences, so here comes the IoT mobile application architecture, which fulfills all these gaps which we discussed. And limitations of industrial gateway. In a popular approach, most industrial gateways directly connect with enterprise systems. Like customer needed to customize. If a customer needs customized gateways as per their IoT devices and applications, hence the direct connections to the enterprise systems are not helpful. So for these kind of things, the software tailoring in gateway is slow down IoT solutions development and deployment process. It also increases cost at every stage of the IoT product lifecycle. The situation is impeding the growth of IoTs, and moreover, latency, easy and quick integrations as well as configuration of the devices, uninterrupted operations, and valuable user interfaces or other challenges. These are the other challenges with the industrial gateways. And so the solutions to all these challenges is a low power, ubiquitous, last inch networking approach facilitated by Wi-Fi and BLE. That's a Bluetooth. Almost all smartphones have these inbuilt in them to support Wi-Fi and Bluetooth. And the global networks of cellular networks can easily fulfill all the limitations, and it can bridge all the gaps in the connectivity, in, Wi-Fi connectivities, limitations of industrial gateways. Hence, when you use the mobile as an IoT gateway, can take IoT solution development and deployment to a next level in the usage. Applications of mobiles as an IoT gateway. So ambient data collection also, and multi-platform connectivity, masking industrial gateway failures. So these are the applications of mobile as an IoT gateway, like ambient data collection. So normally, poor connectivity, expensive data links, or device power constraints or barriers in a normal data collection devices. So for because of this, the data retrieval from each devices is a challenging one. So a network of sensors can allow data packets to hop through the network. So if you have a huge amount of sensors in a factory, for example, and if you want to have a connect and take data from it, we need to have a gateway connections, so proper network connections. The solution often does not work in areas with the challenging RF characteristics. So in normal contrast, IoT mobile app architecture leverages smartphones' inbuilt capacities of data collection from installed sensors. Consider old buildings or legacy machines with poor RF characteristics. Through those sensors are deployed, data collection seems very challenging uh, because if it's a legacy machines, it will be very difficult to collect data. It will be very slow, and the processing of the machines will be very slow. The facilities manager can easily use uh, daily occupants integrated IoT mobile apps, their permissions, and so this is one way of using if you have mobile devices, you need not go for a very costly industrial gateways. So the mobile device and application on it will be able to act as a gateway and collect all the data and process it. Multi-platform connectivity, like connecting multiple devices, like for example, Apple Watch pairs with the iOS device, Motorola and Samsung watches also follow a similar model. Also, we have a brand-centric closed flow approach is a barrier to the potential usefulness. Like Apple watches only connect with Apple devices, like we saw, and you cannot take the data out of the Apple cloud sometimes. And you have to whatever data, various types of data as you use iPads, um, iMobile, Apple mobiles, and other Apple devices, Apple MacBooks. So data within them will be in their network, separated, secure network. So you cannot use it across other Windows operating systems sometimes. And this is a multi-platform connectivity things. So when I open IoT architecture using mobile as a gateway, any smartphone can ask any smartphone to act as a gateway. It is useful for applications that are running on devices that consume very low bandwidth internet, and this is also very valuable for making IoT applications available to large group of people in a cost-effective manner, masking industrial gateway failures. So what happens here is in an industrial gateway faces either external or internal damages and loses its ability to send or receive data. Then an open gateway IoT architecture allows devices to use any smartphone to forward and receive data in situations where a smart wireless glucose monitoring system is used. It is very crucial to not to lose a functionality because of any error in the industrial gateways. Using mobile as a gateway is a very useful and vital one in the IoT architecture, mobile IoT architecture. So IoT is important when peripheral nodes request an acknowledgement, TCP or UDP facilities it in near real time. So to conclude, what happens is mobile as a gateway enables an open IoT uh, structures and promoting the development and growth of IoT networks quickly. And next topic is the role of integration or tools such as MQTT or CoAP. So what is the difference between MQTT and CoAP? And MQTT is a client-server protocol designed for the Internet of Things, which publish subscribe messaging as its core. MQTT server, also known as the MQTT broker, allows you to inspect and manage connected iOS devices and messages. The broker can also provide shared services such as retain messages. There are many client libraries and brokers available, like free or open source and commercial supported applications. What is SCOPE? The Constrained Application Protocol. Is also a client-server protocol designed mainly for Internet of Things. It's also targets constrained devices, but is modeled on the World Wide Web of resources, URLs, and HTTP. It uses get, post, put, and delete verbs like HTTP, which can interoperate with through proxies. URLs represent device state, but devices can be a client or server. And which it can incorporate with through proxies. URLs represent device state and also, but devices can be a client or server. For example, a client posts updates to the server or server responds to get a request from the client. So MQTT is a layer over TCP, whereas CoAP works over UDP. Some features of TCP that are not in UDP, such as fragmentation, and have to be re-implemented in CoAP. On the other hand, CoAP is able to use the multicast feature of UDP, which does not exist in TCP. Like MQTT, CoAP has implementations of client and servers in multiple languages. So, what is MQTT? MQTT is a communication protocol which with features specifically targeted at IoT solutions and uses TCP connections for reliability, fragmentation, and ordering. Aims to minimize the data overhead of each MQTT packet, can store last known good data value for a device, and can send notifications when clients unexpectedly disconnect to allow client state to be monitored. Uses bidirectional message flows. Data from commands to devices can use the same TCP connections, and employs publish or subscribe routing, which makes it easy to add more consumers and producers of data. So MQTT commands or connect, subscribe, publish, unsubscribe, and disconnect. So topics are the distribution units to which clients can push or subscribe. All authorized subscribers to a topic will receive all messages published to it. MQTT topics do not have to be predefined. Applications can create them simply by using the MQTT protocols. What is SCOPE? RFC 7252 defines the core of the COAP protocol. It was designed for machine-to-machine applications such as smart energy and building automation, supporting constrained devices and networks, while cooperating with HTTP through simple proxies. Scope reuses the web concepts of URLs and internet media types to enable the building of IoT solutions. The core interactions between client and server is request response. This is the MQTT and COAP comparison summary. So, what is the full name? What is that? So, architecture, how it works, the command targets, underlying transport protocols, default and secure TCP ports, and secure UDP ports, secure connections, like this. So, when it comes to MQTT performance versus scope performance, um, this is an approximate pocket sized, like with the Wireshark normally. UDP's overheads of for a payload of 256 bytes, and MQTTs establish connections with 166 bytes, subscribe 159, and COPE UDP none. For each message published, 388 bytes, and 312 plus 75 request plus response uh, COPE bytes, and some for one message is 1101, and for COPE is 387. This shows a number of messages and the protocol and messages per second it transfers an average round trip time. Next is advantages and disadvantages of MQTT. Having a centralized MQTT broker means that IoT services are available in a ready-made and portable form. So, applications can track messages and communicate the availability of services. Retained messages provide the last known bit value for data stream. One of the greatest attributes of MQTT is the flexibility with which you can create solutions. The publish subscribe paradigm allows many clients to produce and share information with each other, as well as back-end systems. Brokers can be chained together, and the MQTT gateways connected to the cloud services just by mapping the flow of messages through topics. So inbuilt queuing of MQTT brokers can deal with the connection interruptions and provide buffering for constrained devices that don't have the capacity to do it by themselves. So advantages in the of COAP, which is COAP behaves similarly to HTTP, which is familiar to many developers and users. Whether that shoots more or less than MQTT, publishers subscribe can be a matter of taste. And also with COAP using UDP, it has smaller overheads than TCP, but a smaller maximum payloads and less reliability. It can use the multicast ability of UDP for certain efficient functions. COAP was designed for IoT, so it does a good job of supporting low powered devices. Some downsides of COAP using UDPs are it can be more difficult to traverse firewalls. So, and unlike MQTTs that uses web sockets, it can be used in DDoS attacks if internet facing. And CoAP solutions are very flexible since definitions and of client and server are dynamic. In MQTT, these elements are fixed. That also means no CoAP standard brokers exist with general services that can be relied on. The next topic is mobile technology for supporting IoT ecosystem. So, in this, mobile technologies for IoT ecosystem include cellular IoT standards like 5G, LTE, M, Volt, NB IoT for long range, low power connections, as well as short range technologies like Bluetooth and Wi-Fi for local device communications. Mobile devices act as gateways and as a user interfaces for IoT devices using open protocols and multi-protocol integration to provide control, monitoring, and data sharing across the ecosystem or across the network. And cellular IoT technologies. These technologies uses existing mobile networks to connect to IoT devices. Those are like 5G offers high speed, ultra low latency, and the ability to support massive number of connected devices, and makes it ideal for advanced IoT applications. LTEM, like LTE CAT M1, the low power wide area network LPW, LP-WAN, optimized for mobile IoT, providing better coverage than NB IoT and supporting SMS and mobility. NB IoT narrowband IoT, another LP-WAN technology designed for devices that require long battery life and extensive coverage, but it is not suitable for mobile applications or SMS. Short range technologies, these technologies connect devices over short distances. That those are Wi-Fi, Bluetooth, NFCs. Wi-Fi efficient for short range local connections with new standards like Wi-Fi 6 offering faster and more reliable communications for IoT devices. Bluetooth, especially Bluetooth Low Energy or BLE, a low power standard preferred for battery powered devices such as smart home sensors and asset trackers. NFCs, it is a near field communication, which enables instant low power short range communications for tasks like less contactless payments and ticketings and etc. And role of mobile devices and apps, the mobile devices act as a gateway, user interface, multi-protocol support, data sharing. What is gateway? Smartphones and other mobile devices can serve as gateways for IoT devices, connecting them to the internet and larger networks. And user interface mobile apps are used to control and monitor IoT devices, providing an interface for user interactions. Multi-protocol support mobile devices often support multiple connectivity protocols, cellular, Wi-Fi, Bluetooth, NFCs, making them versatile for diverse IoT setups. And data sharing. So in this data sharing, mobile apps can integrate with third-party applications to share and utilize the data collected from IoT devices, enhancing the IoT ecosystem's capabilities. So, so that's all for now. Thank you all for joining the class today.